What if I told you there's a metal that can't be destroyed by fire, pressure, or time? A material without which aviation would grind to a halt, lights would go dark, and rocket engines would fall silent. And here's the thing, it's so rare that the entire world is competing for every single gram. Tungsten has the highest melting point of any metal on Earth, a staggering 6,192 degrees Fahrenheit. That's a temperature at which most other metals would have long since turned to vapor. Annual global tungsten production ranges from 85 to 100,000 tons per year. But here's what's striking. Up to 40% of all tungsten consumed worldwide comes from recycled material. That's a massive number, showing just how valuable it is. Total global tungsten reserves are estimated at roughly 3 to 3.5 million tons, nowhere near the reserves of iron or aluminum. But here's what really matters. By the end of this video, you'll learn a secret about tungsten that the industry hides and almost nobody talks about. Something that will flip your understanding of the metal-holding civilization together. Picture a massive underground mine somewhere in Vietnam, China, Russia, or Canada, the world's biggest tungsten producers. Deep in the Earth's belly, hundreds of feet down, lie ores containing tungsten. Not pure metal, but complex minerals, wolframite and scheelite. Wolframite is a compound of iron, manganese, and tungsten. Scheelite is calcium tungstate. Geologists use various methods to identify and assess tungsten ore deposits. Then, using powerful drilling rigs and explosives, the ore is extracted from deep underground. It's tough, dangerous work, requiring high-tech equipment and strict safety standards. Thousands of tons of ore get hauled to the surface daily by massive underground trucks. Powerful blasts shatter the rock, exposing the valuable ore. It's like a controlled earthquake in miniature. After the blast, the ore gets loaded into haul trucks with capacities up to 300 tons and transported to the processing plant. After extraction, the ore goes to a processing plant. Here it undergoes several stages to separate valuable wolframite or scheelite from other rocks. First, the ore is crushed in crushers and mills into a fine powder. Massive jaw crushers with deafening roars break down car-sized chunks into fist-sized pieces. Then the crushed ore enters ball mills, giant rotating drums filled with steel balls. In these mills, the ore is ground into an extremely fine powder, almost like flour. Next, various enrichment methods are applied, such as gravity separation, magnetic separation, and flotation. Gravity separation uses the difference in density. Tungsten minerals are heavier than waste rock. Magnetic separation separates weakly magnetic wolframite particles from non-magnetic impurities. Flotation is a process where the ground or powder is mixed with water and special chemical reagents in large tanks. These reagents selectively attach to tungsten mineral particles, making them water repellent. Air is then pumped through the mixture, creating millions of tiny bubbles. The tungsten mineral particles latch onto these bubbles and rise to the surface, forming a foam. Other unwanted minerals stay at the bottom. This enriched foam is collected. These processes yield a concentrate containing 60 to 70% tungsten trioxide, which is an intermediate form. The resulting concentrate is then processed at metallurgical plants to obtain pure tungsten. This is a complex chemical process that can involve alkaline leaching, precipitation of ammonium paratungstate, and its subsequent calcination to produce tungsten oxide. The concentrate is dissolved in alkaline solutions at high temperatures. Ammonium paratungstate, an intermediate compound, is then precipitated from the solution. This compound is calcined at temperatures around 1100 to 1500 degrees Fahrenheit, producing tungsten oxide, a yellow powder. Tungsten oxide is then reduced to metallic tungsten by heating it in a hydrogen atmosphere at temperatures ranging from 2000 to 3300 degrees Fahrenheit. Inside specialized furnaces, tungsten oxide is heated in a stream of hydrogen. The hydrogen strips away oxygen from the tungsten oxide, releasing pure metallic tungsten. The result is a fine gray tungsten powder, the foundation for every product that follows. It's from this powder that tungsten rods, bars, and other blanks are formed through sintering. The tungsten powder is pressed under high pressure into the desired shape, then sintered at extremely high temperatures in a hydrogen atmosphere. This allows the powder particles to bond together, forming a dense, durable material. Sintering temperatures can reach 5400 degrees Fahrenheit. At that temperature, the powder particles begin to fuse, creating a monolithic structure. The process takes place in furnaces with controlled atmospheres to prevent oxidation. One of the most critical applications is the production of hard alloys known as tungsten carbides. These alloys, combining tungsten with carbon, plus cobalt or nickel as a binding agent, rank among the hardest man-made materials. Tungsten carbide is created by heating tungsten powder with carbon at temperatures around 2500 to 2900 degrees Fahrenheit. Tungsten carbide crystals form, which are then ground into powder. This powder is mixed with cobalt or nickel, serving as a binder, pressed into molds, and sintered. Tungsten carbides are used to manufacture cutting tools, drill bits, milling cutters, lathe tools that can machine the hardest metals and alloys. Without tungsten carbides, modern mechanical engineering, metalworking, and oil and gas extraction would be impossible. 2 pounds of tungsten can become a drill bit capable of boring thousands of feet through rock, demonstrating its incredible efficiency. Tungsten is also widely used in the military industry for manufacturing armor-piercing shells and bullet cores. Thanks to its high density and hardness, tungsten alloys have excellent penetration characteristics, providing high effectiveness against armor. It's also used in heavy armor plating and counterweights. In electronics and electrical engineering, tungsten is irreplaceable. It's used to produce filaments in incandescent bulbs, welding electrodes, electrical contacts, and other components requiring high heat resistance and electrical conductivity. Because of its high melting point, it's used in the space industry for components subjected to extreme temperatures. High-temperature alloys containing tungsten are used in aircraft engines, turbines, and other devices operating under conditions of extreme heat. Alloying with tungsten increases the heat resistance of other metals. In medicine, tungsten is used in manufacturing X-ray tubes thanks to its high atomic number, which effectively blocks X-rays. It's also used in radiation shielding, similar to lead, but with lower toxicity. Plus, tungsten is used to create ballasts and counterweights in race cars, aircraft, and yachts thanks to its high density. It's also a component in certain jewelry pieces because of its hardness and scratch resistance. Tungsten is one of the least abundant elements in Earth's crust, which makes its mining and production especially valuable. Global tungsten reserves that are economically viable to mine are estimated at roughly 3 to 3.5 million tons. However, when you factor in potential but not yet explored resources, the total volume could be significantly higher. This is, of course, incomparably less than reserves of metals like iron or aluminum, which underscores its strategic value. Annual global tungsten production, measured in tons of pure metal or tungsten oxide equivalent, fluctuates, but in recent years it's been approximately 85 to 100,000 metric tons per year. This figure includes both primary extraction from ores and recycling, which is becoming increasingly important. Imagine being able to take a worn-out tool that's already served its purpose and turn it back into something new, without spending energy and resources mining ore from scratch. That's exactly what happens with tungsten. Tungsten recycling is among the most advanced and efficient of all metals. By various estimates, up to 40% of all tungsten consumed worldwide comes from recycled material. That's a massive number, demonstrating its value and economic viability. Where does used tungsten come from? The main source of secondary tungsten material is, of course, spent cemented carbides. Those cutting tools, drill bits, and milling cutters made from tungsten carbide. After intensive use, they wear down, lose their edge, or break. Instead of tossing them in a landfill, they're collected and sent to recycling plants. Other sources include tungsten-containing scrap metal, leftovers from tungsten product manufacturing, plus certain electrical contacts and wires. Recycled tungsten is significantly cheaper to produce than primary metal because it eliminates the expensive and energy-intensive stages of ore mining and initial processing. Recycling dramatically reduces tungsten production's environmental footprint. It minimizes the need for mining operations, cuts energy consumption, reduces industrial waste, and lowers greenhouse gas emissions. This makes production greener and more responsible. And so, after a journey from underground blast through grinding into powder, and through flotation with millions of bubbles, through chemical dissolution and reduction in a hydrogen atmosphere at 1800 degrees, through sintering at 3000 degrees, a metal is born with the highest melting point on Earth, capable of withstanding 6192 degrees Fahrenheit, a metal without which modern industry, aviation, aerospace, and medicine would be impossible. And the most remarkable part, nearly half of this metal is born anew from old tools, making tungsten one of the most environmentally friendly strategic materials of our civilization.
But an 80,000-ton press isn't just about aviation and space, it's about energy. Massive shafts for hydro turbines, rotors for nuclear reactors, high-pressure housings, all of this demands single-piece forgings of monstrous proportions. Picture a hydro turbine shaft 50 feet long and over 6 feet in diameter. Its weight, more than 100 tons. You can only forge a component like that on a super powerful press. The blank gets heated in a furnace the size of a house, then a crane transfers it onto the press platen, and in just a few strikes, it's shaped into form. Each strike, 80,000 tons of force molding the metal, densifying its structure, squeezing out internal defects. After forging, the part cools slowly, then undergoes heat treatment and machining, but the foundation of its strength, that's laid right there on the press. $80,000 tons. Picture a force that could crush 10 tanks at once. A machine tall as a 10-story building that transforms a red-hot steel mass weighing hundreds of tons into a flat panel like it's Play-Doh. This isn't science fiction. It's the world's most powerful forging press, operating in China since 2013. 80,000 tons of pressure. That's more than the weight of 50,000 cars crashing down on a piece of metal the size of a table. Why did humanity need such monstrous machines? What secrets hide in their history from the Cold War? How did the USSR create a 75,000-ton monster and the US answer with a 50,000-ton press? You'll discover how these metallurgical giants were born, how this inhuman force works, and what can be done under such pressure. Watch till the end. The finale reveals the scale of what humanity creates. The story of giant forging presses didn't start with peaceful purposes. It started with the Cold War arms race. In the late 40s and early 50s, aviation and rocketry demanded fundamentally new solutions. Aircraft were getting bigger, faster, flying higher. Rockets grew in size. And all of this required enormous single-piece components made from high-strength alloys. Titanium wing spars, aluminum fuselage panels, steel rocket engine parts. Welding these components together from multiple pieces weakened the structure. Welded seams were vulnerable under load and vibration. What was needed was a technology capable of forging a giant part as a single piece, no seams. That's how the idea of ultra-powerful hydraulic presses was born. The United States understood this first and built several presses in the 50s, capable of exerting up to 50,000 tons of force. The Soviet Union wasn't about to be left behind. At the height of the space race and the arms race, the USSR built a 75,000-ton forging press, an absolute record at the time. The giant machine stood in the factory floor like a metal cathedral, dozens of meters tall, hundreds of tons of structure, hydraulic cylinders as thick as a human body. This press allowed the Soviet Union to stamp out parts for rockets, submarines, and aircraft on a scale that was previously impossible. A solid titanium component several meters long, no longer a dream, but reality. 75,000 tons of force meant that metal of any hardness became pliable material. The Cold War fueled technological progress, and these forging giants were one of its symbols. For decades, these presses remained the pinnacle of engineering. But in 2013, China shattered all records. At one of their metallurgical plants, they fired up a hydraulic press with a force of 80,000 tons. 80,000 tons? That's a force that's hard to wrap your head around. It's the weight of a major ocean liner crashing down on an area the size of a dining table, or pressure equivalent to 50,000 cars stacked on top of each other. The scale of this press is mind-blowing, as tall as a 10-story apartment building, weighing thousands of tons of steel and cast iron, with massive hydraulic systems capable of generating this monstrous force. This press didn't just break a record, it opened up a whole new era of possibilities. Now you can stamp out parts of sizes that used to be considered impossible. Panels for jumbo jets, components for space rockets, reactor equipment, all of this became achievable thanks to this machine. How does a giant like this work? The foundation is hydraulics. Picture massive cylinders filled with oil under monstrous pressure. When pressurized oil flows into the cylinder, the piston starts to move. But this isn't your ordinary piston. Its diameter measures in yards, and its stroke spans dozens of yards. Slowly, but with unimaginable force, the piston descends to where a glowing metal workpiece sits on a massive plate. The workpiece weighs hundreds of tons, a huge ingot of steel, titanium, or aluminum, heated to around 2200 degrees. The metal glows bright orange, radiating unbearable heat. The shop floor fills with the roar of hydraulics, the smell of hot metal and oil. And then, the upper plate of the press begins its descent. Slowly, almost ceremonially. But behind that calm lies 80,000 tons of force. Contact. The upper plate of the press touches the red-hot blank, and the miracle of deformation begins. Metal that's hard as rock at room temperature starts flowing like thick paste under this kind of pressure. 80,000 tons don't give the metal a choice. The blank flattens, spreads outward, takes the shape of the die. A thick ingot becomes a flat panel or a complex three-dimensional part. The process is accompanied by deafening thunder. The metal cracks, groans. Excess material squeezes out, flowing to the sides in glowing streams. Temperature, pressure, force, all controlled by computers with millimeter precision. The slightest mistake and a multi-ton blank is ruined, or worse, the press itself can fail. But the operators know their craft. One stamping cycle takes minutes, but the result is a seamless part with perfect internal structure. Why does this matter so much? Because a single forged part is stronger than any welded structure. A weld seam is always a weak point. Under load, vibration, cyclic stress, that's where cracks start. In aviation or spaceflight, a crack means catastrophe. That's why major structural elements, aircraft wing spars, fuselage panels, landing gear components, rocket engine parts, must be one piece. A super heavy press can forge a titanium beam 30 feet long with no joints whatsoever, or an aluminum panel the size of half a Boeing wing, or a steel blank for reactor equipment weighing 400,000 pounds. Parts like these used to be welded together from dozens of pieces. Now they're made in one press stroke. It's a revolution in manufacturing.
China didn't build this press by accident. The country is aggressively developing its aviation industry, space program, and nuclear power. All of this demands technologies that were previously only available to the US and Russia. An 80,000-ton press is a declaration of technological leadership. Now China can manufacture components it used to have to buy from abroad or settle for smaller dimensions. This is strategic independence. When you've got a press like this, you can build your own aircraft, your own rockets, your own reactors without relying on someone else's technology. It's no coincidence that information about the exact specs and capabilities of this press is tightly controlled. This isn't just manufacturing equipment, it's an element of national security and technological sovereignty. There are only a handful of these presses in the world. Russia has kept its Soviet-era 75,000-ton giants still running in defense plants today. The US operates its 50,000-ton machines, built back in the 50s and 60s. China now leads with 80,000 tons. There are projects for even more powerful presses, 100,000 tons and beyond. But each of these machines represents a colossal investment. Building a super heavy press costs hundreds of millions of dollars. You need a special foundation that goes dozens of feet into the ground. You need massive hydraulic systems, furnaces to heat the billets, cranes with lifting capacities in the hundreds of tons. It's an entire complex covering the area of a football field. But the payoff is worth it, the ability to manufacture parts that nobody else can. And just like that, through the Cold War, through the technology race between superpowers, through decades of engineering development, humanity arrived at the 80,000-ton press. This isn't just a machine, it's a symbol that we've learned to dominate matter with a force comparable to geological processes. When 80,000 tons come crashing down on white-hot metal, it's like watching the Earth's crust crumple into mountains under tectonic plates. Except here, this process is controlled by humans. Every part that comes out of a press like this carries the imprint of unimaginable force and precision. Planes fly, rockets shoot into space, reactors generate power, and behind all of it stand these giant presses, crushing metal like Play-Doh. This is the story of how humanity learned to create the force of gods and use it to conquer the sky, space, and the atom.
Picture this, 8% of all CO2 on the planet comes from one industry, steel. Every single second, the world produces 60 tons of steel, and every ton leaves behind nearly 2 tons of carbon dioxide. But in Sweden, something seemingly impossible happened. They made steel without coal, zero coal. Instead, hydrogen and electricity. Sounds like science fiction? In 2021, a Volvo truck built from this steel hit the roads. The first vehicle in history made from steel with a zero carbon footprint. How is humanity walking away from a technology that's 3,000 years old? You'll learn why traditional steelmaking is killing the planet, how hydrogen is replacing coal in blast furnaces, and why this revolution will change everything, from skyscrapers to cars. Watch to the end. The finale will show you that the future of steel isn't black anymore. It's green. The history of steel production began 3,000 years ago when humanity learned to smelt iron. The principle remained unchanged for millennia. Iron ore is heated with coal. Carbon strips oxygen from iron oxide, and you get pure iron. This is called reduction. And the byproduct? Carbon dioxide, which escapes into the atmosphere. For centuries, nobody cared. In the 19th century, blast furnaces appeared, steel giants as tall as a 20-story building. Inside, temperatures hit 3,600 degrees Fahrenheit. Superheated air blasts in from below, while iron ore and coke, specially fired coal, get loaded from above. The ore descends, meets the carbon, and out comes molten pig iron, glowing orange like lava. Pig iron then becomes steel by blowing oxygen through it to remove excess carbon. This technology fueled the Industrial Revolution, built skyscrapers, bridges, ships, automobiles, but it comes with a monstrous cost. Every ton of steel requires about 1,300 pounds of coke. When burned and used to reduce the ore, it produces nearly 4,000 pounds of carbon dioxide for every ton of steel. Global steel production, almost 2 billion tons per year. Do the math, around 7.5 billion tons of CO2 annually. That's 8% of all global greenhouse gas emissions, more than all aviation worldwide. If the steel industry were a country, it would rank third in emissions after China and the US. And the problem's getting worse. Demand for steel is rising, especially in developing countries. By 2050, emissions from steelmaking could double if nothing changes. Humanity's caught in a trap. Modern civilization is impossible without steel, but steel is killing the climate. Aluminum or plastic can't replace steel in most applications. The properties are just too different. We needed a revolution, and it started in cold Sweden, in the city of Luleå, above the Arctic Circle. In 2016, 3 Swedish companies, SSAB, Vattenfall, and LKAB, announced the launch of the Hybrid project, Hydrogen Breakthrough Iron-Making Technology, a breakthrough technology for producing iron with hydrogen. The idea seemed insane. Replace carbon with hydrogen in the ore reduction process. Instead of the iron plus carbon reaction that produces CO2, use iron plus hydrogen, which gives you H2O, water, just water, no carbon dioxide. But the challenge was titanic. They needed to build a hydrogen production plant using electrolysis, powered by renewable energy. They needed to design direct reduction reactors that use hydrogen to process iron. They needed to prove this iron could be transformed into quality steel and make all of it economically viable. 5 years of work, hundreds of millions of euros in investment. In June 2021, they fired up the world's first hydrogen-based steel plant in Luleå, a pilot facility, but fully operational. The revolution had begun. Now let's break down how this actually works. The process starts with hydrogen production. Typically, hydrogen comes from natural gas, but that creates CO2 emissions. Hybrid uses water electrolysis. They run electric current from wind and hydroelectric plants through water. The water splits into hydrogen and oxygen, pure green hydrogen, zero emissions. This hydrogen feeds into a shaft furnace, a direct reduction reactor. Iron ore pellets get loaded from the top. These are walnut-sized granules made of iron oxide. Superheated hydrogen enters from below at around 1500 degrees Fahrenheit. The hydrogen rises up through the pellet bed. A chemical reaction occurs. Hydrogen strips the oxygen from the iron oxide. What forms is metallic iron and water vapor. Yep, just steam. The pellets sink downward, gradually losing oxygen and transforming into porous iron, called sponge iron or direct reduced iron, DRI. What comes out are gray, porous granules of pure iron. But this isn't steel yet. The sponge iron gets loaded into an electric arc furnace, a massive steel vessel with graphite electrodes as thick as telephone poles. They run monstrous electrical current through these electrodes, tens of thousands of amps. Between the electrodes and the metal, an electric arc forms with temperatures reaching 6,300 degrees Fahrenheit. That's hotter than the surface of the sun. The iron melts in minutes. They add alloying elements, chromium, nickel, molybdenum, to get the exact grade of steel they need. The electricity for the furnace also comes from renewables, hydroelectric plants, and wind turbines. The molten steel glows blindingly white. They pour it into molds, let it cool. What you get are steel ingots or billets, indistinguishable in properties from conventional steel, but their carbon footprint, practically zero. The entire process uses not a single ounce of coal, not a single ounce of coke, not a cubic foot of natural gas, just iron ore, hydrogen, electricity, and water. This is fossil zero metallurgy. In August 2021, a historic event occurred. The company SSAB shipped its first batch of green steel to a customer. The buyer was Volvo. This steel was used to manufacture body parts for trucks. The first vehicles in human history made from carbon-free steel. Volvo ran tests: strength, fatigue resistance, weldability, corrosion resistance. All parameters identical to regular steel, or even better. Because the process is more controlled, fewer impurities. In 2022, other companies also received batches of green steel. Manufacturers of excavators, construction equipment, household appliances. Mercedes-Benz ordered a batch for use in passenger cars. SSAB announced that by 2026, it will launch the first full-scale hydrogen-based plant. Capacity, 1,300,000 tons of steel per year. By 2035, all SSAB products will be carbon-free. The company promises to cut Sweden's emissions by 7% just by switching to hydrogen. But hybrid isn't the only project out there. Right there in Sweden, they're building the H2 green steel plant, 5 million tons per year. Launch is set for 2025. In Germany, ThyssenKrupp is converting its blast furnaces to hydrogen. Austria's voestalpine fired up a pilot hydrogen plant. South Korea's POSCO is pouring billions into the technology. Even China, the world's biggest steel producer, announced it's building hydrogen plants. Governments are backing the tech with subsidies and tax breaks. The European Union rolled out a carbon tax on steel imports. More emissions, higher tariff. That makes green steel competitive. The big problem right now? The cost of green hydrogen. Hydrogen from electrolysis is still pricier than hydrogen from natural gas, but prices are dropping. Over the last 10 years, the cost of electrolysis fell by 2/3. As renewable energy capacity grows, hydrogen will get cheaper still. Another advantage of hydrogen metallurgy? It's way more compact. A traditional steel plant is an absolute monster of a complex. Coking plants, sintering factories, blast furnaces, converters, rolling mills, all of that eats up miles of land. A hydrogen facility is much tighter. An electrolyzer to produce hydrogen, a shaft furnace to reduce the ore, an electric arc furnace for melting. You can build a plant right next to your iron ore source and renewable energy, instead of hauling raw materials halfway across the globe. Swedish projects use ore from local Kiruna deposits, one of the largest in the world, and electricity from hydroelectric plants and wind farms in northern Sweden. Logistics get simpler, costs drop. Steel quality can be higher too. Direct reduction with hydrogen gives you purer iron with less sulfur, phosphorus, and other nasty impurities. That steel's better suited for high-strength applications: aviation, cars, bridges, wind turbines. Ironically, the green technology turns out to be technically superior as well. Sure, there are challenges. Hydrogen metallurgy demands massive amounts of electricity. Producing 1 ton of steel requires about 3.5 megawatt-hours of power. That's a small city's daily energy consumption. That's why projects are being built where cheap renewable energy is abundant. Scandinavia with its hydroelectric plants, Germany and Denmark with wind, Australia with sun. You also need infrastructure for storing and transporting hydrogen. It's an explosive gas. They're building special pipelines, storage tanks, safety systems. But all of this is solvable. The technology exists, the economics are starting to add up, and so is the political will. Analysts predict that by 2030, 10% of the world's steel will be produced with hydrogen. By 2050, a third or even half. That'll cut CO2 emissions by 1 billion tons annually, like removing 200 million cars from the roads. The metallurgy revolution, quiet but powerful.
And just like that, journeying from ancient blast furnaces where iron was smelted with coal 3,000 years ago, through recognizing an environmental catastrophe and searching for solutions, humanity arrived at hydrogen, the most abundant element in the universe. The very same gas that stars are made of now melts steel on Earth. Instead of black smoke from blast furnace stocks, water vapor. Instead of billions of tons of carbon dioxide, water. This is a story about how a technology that seemed unshakable was rewritten in a decade. Every time you see a new skyscraper, bridge, or car 10 years from now, know this: inside, possibly, green steel. Metal produced without harming the climate. The metal of the future, made from ore, water, wind, and sun. Black metallurgy is turning green. And this isn't just a color change, it's a paradigm shift. Humanity has proven you can build civilization without destroying the planet, even in an industry as dirty as steel. The hydrogen revolution has begun, and it will change everything.